Good morning, good afternoon, or good evening, wherever you may be in the world. Thank you for joining us today. My name is Joy Bastaros, and I'm going to be your webinar host for the day, coming to you from Houston, Texas, here in the United States. I'd like to formally welcome you to today's Siemens Global webinar. Our topic for the day is Innovate Swiftly and Architect Resilient Cooling with HVAC CFD Software. I'd like to welcome today's speakers. We have Mr. Chris Watson. Chris is the Technical Manager for Simcenter FloEFD products for the Mechanical Analysis Division of Mentor Siemens. He is responsible for technical leadership of Mentor's FloEFD product line in North America. His engineering roles through the years have included consulting, technical support, customer training, and pre- and post-sales application engineering. Currently, he works in the software development group to help influence the direction of FloEFD and promote its growth in North America. Welcome to you, Chris. We also have with us today Mike Grutzmacher. Mike has a graduate engineering degree in mechanical engineering from F.H. Bochum and did distance study business economics for engineering as well. He spent 6 years as an application engineer for FloEFD for Mentor Graphics, 2 years as a project engineer for industrial engineering at H.P. Pelzer Group, and 8 years as a project manager for waste heat recovery systems, Kutner Energy and Environment. Since April of 2015, he has held his current role as the FloEFD product specialist here at Siemens. Happy to have you both with us today.
Great. Okay. And yes, thank you all for joining as well and taking some time for this webinar today. Let's start by covering what we're going to talk about today. So we'll start with briefly discussing some business challenges, both generally and as they relate to the HVAC space. Talk about Siemens front-loading approach and introduce FloEFD as the CFD product that addresses that, and extend on that a bit, discussing the HVAC module of FloEFD, discuss some areas, some applications where FloEFD can be applied in the HVAC space, and then go through some examples showing FloEFD in action as it's used to address some of these different application areas. Finish up with some customer successes, and then have a Q&A session at the end, as Joy mentioned. Okay, so let's begin by looking at some topics or categories as they relate to understanding and improving your HVAC system. So we'll start with a couple of anecdotes on the economic impact related to HVAC. So take a system that uses fans to drive flow. If you can cut the volume flow rate requirement of the system in half, meaning that the fan would only need to supply half the flow rate, you would reduce the electrical energy consumption of that fan by 7/8. So it would require only 1/8 of the original energy to drive the fan. Similarly, in a heating application, reducing the air temperature requirement of the space by 1 degree Celsius can save 6% heating energy. So these are just a couple examples. They're sort of based on rules of thumb, but they clearly there is an economic motivation to improve HVAC performance. So now let's look at another role of an HVAC system, which is to ensure the performance and reliability of the relevant equipment that it relates to. So let's take, for example, a data center. So obviously the electronic equipment in a data center needs to be kept within a certain temperature range to operate reliably and not to have failures. So of course you rely on your HVAC system to keep it in that operating range. So certainly HVAC then is an important portion of your business as it relates to the performance of this electronic equipment. There's lots of other examples related to performance that you could cite. If you move to comfort, for instance, obviously that's one of the key parameters that you have an HVAC system to begin with for is to provide comfort for the inhabitants in a space. So certainly residential or commercial spaces. And one of the ways that people judge or they are satisfied with the space that they're in is related to the comfort that they feel in that space, and that relates to the HVAC performance. Similarly, on the transportation side, in your car, for instance, your comfort level definitely relates to your overall satisfaction with that being in that vehicle, and of course that's related to the HVAC system. And on the health and safety side, there's impact related to HVAC. So applications like clean rooms or operating rooms in hospitals, where you need to sort of manage contaminants or ensure a sterile space. That's going to be through your HVAC system. So this just starts to introduce some topics and some motivations for being able to understand and simulate and optimize your HVAC system. So if we then move just more generally and look at, there was a study done by Aberdeen a few years ago, and they asked companies to list out their top 5 hurdles for product design, which is that graph you see there on the left, as well as to list their best-in-class strategies to improve the design process. Really, in terms of the top 5 hurdles, the first thing, the thing that rose to the top is this idea that problems or errors in your design, being found out too late, being sort of the number one impediment to your design process. As I move down a little bit, I see the third one there, frequent design changes, as another issue. So certainly those are topics that you'd want to address. And if you look at how these companies, what strategies they use to improve their design process, and in that graph they break it out by best-in-class companies versus the rest, you see that number one there is this idea of being able to analyze product behavior earlier. So clearly this is an issue overall in the design process, is just being able to get this earlier feedback. And to do that, when we say analyze product behavior earlier, it's going to be really through simulation. The earlier you move in the process, it's inefficient and time consuming to try to rely on physical testing, or other means don't fully capture the problem well enough. So you get to the point where relying on simulation and being able to move it early in the process is advantageous and desirable. So that move and that notion is what we refer to as front loading. So let's go ahead and expand on that a little bit, what the Siemens approach to front loading is all about. So and in our case, of course, we're going to be in the HVAC space talking about CFD. And if you look at the overall design process, as you move to the right, making changes to your design becomes more and more costly, as opposed to being able to do some of this optimization earlier in the process. So the cost to fix defects rises as the design proceeds to the process, and any of these failed prototypes are costly and result in missed milestones. So if you can, and what we do here at Siemens is have this notion of a digital twin, is in a CAD embedded way be able to simulate your design early and get a sense of the performance of it, where it's still easy to make changes. And ultimately, the most effective approach to that, in our opinion, is to be able to put this technology in the hands of a broader group of engineers who are directly responsible for the design working in CAD, to be able to do some of this work themselves in these early phases. So the tool of ours that addresses that early CAD embedded front loading would be Simcenter FloEFD. And so FloEFD is a general purpose CFD tool. So CFD, of course, is computational fluid dynamics. So that's this virtual simulation of fluid flow and heat transfer. And FloEFD, can address a range of industries. You see, various of the classic industries that are that CFD is used in. But the focus of today's discussion, of course, is going to be on the HVAC space. And we have a long history, working with companies in this industry. So what is it about FloEFD that makes it unique, that makes it suited to be able to realize this front-loading notion? The first, and probably the most obvious when you initially see the software, is just the way we work in CAD. This, the CAD embeddedness, and then ultimately the ease of use and productivity advantages that come from this approach that we take with respect to working with a CAD model. Now, if that's that alone, though, is not complete in sort of solving this problem of front-loading CFD into the early design process by a broader group of engineers. A lot of our users aren't, let's say, classic CFD analysts who specialize in this field. So we need some additional technology, and a lot of it is sort of under the hood and a little more transparent to the user as opposed to this, the CAD embeddedness aspect of it. But some of these unique approaches that get you through the rest of the design process and being successful with doing CFD. So we certainly take a traditional 3D CFD approach for the bulk of the way the software works, 3D CFD approach. But we augment that with a variety of unique empirical and analytical methods, and I'll expand on that here a little bit more. And included in that is the meshing technology, the smart cell technology that we use to capture the mesh, or to mesh and capture these CAD geometries easily without the user having to have had as much experience with doing CFD. So if I just expand a little bit on the CAD embeddedness aspect of it, certainly a good portion of our users, the CAD tool is their environment that they're working in. That's where the design lies, and FloEFD ends up feeling like an extension of their familiar CAD tool. The way you work with the fluid space, and when you're doing CFD, of course, it's the fluid volume that needs to be captured, as well as the solids, is really easy and elegant in FloEFD, and you're actually never going to explicitly extract that flow space yourself. The model is always going to be your native CAD model, and the data is being saved into that CAD model. The input data, the CFD data that you're assigning, and of course the results that you're viewing, you're also doing it in that familiar environment. So you have this native CAD look and feel, which for the CAD designer really adds to the ease of use. And the other aspect about working on the native CAD model includes that you don't really need to simplify this geometry much at all, as opposed to some other CAE methods to get an analysis ready to run. You can really work, for the most part, with the native unsimplified model, and it's the mesher, the strength of the mesher, that actually handles that for you. And then to expand a little bit on those unique technologies that I alluded to, here's just a sampling of some of the key ones. The way that we model the boundary layer, so in fluid flow, capturing this boundary layer at the wall as the flow flows over a surface is key to the overall problem, and it's an area that classically in CFD you'd spend a fair amount of time making sure that that's handled. So we have these sort of more automated technologies that do that, including even somewhat independently of the how dense your mesh is in those regions. If I just pick up another example on here, the thin channels. So typically in CFD, you need a certain number of cells across a passageway, a channel, to resolve the flow well. And if in our mesh, our situation, it's coarser than it should be for classic CFD, we can switch over to these analytical or empirical methods, and that's all done kind of transparently to the user. And for them, at the end of the day, they just have this tool, this engineering tool, in their hands, that they're able to get feedback with good, accurate results of their design early in the process. So just to list out some of the capabilities and the range of physics. And again, this is more broadly, as I mentioned, it is a general purpose CFD tool. So, you know, as you go through here, not all of these would apply to HVAC applications, but many do. Fluid flow, heat transfer, rotating flows, radiation, condensation. So as you work your way down the list, you see a variety of physics and capabilities that apply to HVAC problems of interest. So from that, we can go ahead and take those base capabilities that are in the software and expand on those with a module specific to folks who are running HVAC applications. So let me just touch on what our HVAC module adds additionally to your base package. So you get comfort parameters, the ability to do tracer studies, an additional radiation model, which especially for solar radiation cases is valuable, and it extends the database of material properties that come with FloEFD already. So just to kind of flesh that out a little further, comfort parameters. So certainly when you run a CFD problem, there's a range of various kind of native parameters that you get out of the solution, things like temperatures of the fluid and the solids, and velocities and heat fluxes, etc. So from them, there are a variety of parameters that can be derived that are functions of the flow field and thermal field that you solve that give sort of further insight as to the comfort that an inhabitant in a space might feel. And so here's just a list of them: predicted mean vote, predicted percent dissatisfied, on down the list. So in my example, I'll touch on these in a little more detail. But again, the overall point is being able to assess from a comfort standpoint, more broadly with these parameters. Tracer studies, so these are passive scalars. This is a way of being able to introduce some additional gaseous components into a flow field without needing to include them in the original solution. So you can just solve out sort of the carrier media, if you will, let's say the airflow in a room, and then have some flexibility on the post-processing side to just introduce various gases at different locations and test out different cases without needing to reanalyze anything. So this is just a nice way of being able to track some things like contaminants, smoke, that kind of thing. As I mentioned, another radiation model, what this does is lets you model semi-transparent solids, so you get absorption in solids. This is important for cases involving solar loading. You get added capabilities like wavelength dependency and the like. So a second radiation model that goes along with the one that comes in the base package. And just expanding the library of materials. So you get a list of predefined materials already with FloEFD, and this expands on it, adding materials that are relevant to the HVAC space. So you see, a list here, things like brick and concrete and wood and asphalt, etc. So it's just an added convenience for a user setting up a problem related to HVAC. So what then would be, knowing that and knowing the capabilities of FloEFD, some of the application areas that you could address with the software. So I'm going to divide this into the HVAC space into sort of two categories. One would be HVAC equipment. So the various components that would make up an HVAC system. Certainly there are companies that design and manufacture these devices. So things like fans, compressors, air conditioners, ducts, fume hoods, filtration devices, safety cabinets, blowers, and moving to some additional ones, heat exchangers, pumps, refrigerators, solar heating and renewable applications, valves. So within the HVAC space, there's just a host of equipment that you design where fluid flow and thermal considerations are key, and being able to have software that can do that simulation for you, virtually in your CAD system is really appealing. Now, the other sort of category of HVAC applications would be the built environment. So that's a little different than the equipment, which has sort of more of a classic manufacturing process. This would include things like modeling data centers or clean rooms, or modeling the external flow around buildings, or various of internal spaces within a building, offices, labs, classrooms, or even on a larger scale, simulating full cityscapes. Call out another application area separately here, solar loading, and we'll see that in the example that I go through. So, this certainly impacts the thermal problem for a host of these built environment application areas. And lastly, I went ahead and added this one, which would be transportation. And some folks would categorize this into the automotive space, or aerospace, if it's a cabin comfort for a plane, for instance. But a subset within those industries are still HVAC applications. So certainly the HVAC system in your car could be simulated, cabin comfort. You can extend that to other transportation areas like trains or airplanes. So these are all areas that can be addressed with this type of software, with FloEFD, and the convenience of being able to do it early and by a broader group of engineers. So let's go ahead and look at some examples and start to maybe understand the way that software works a bit more, and sort of get a sense of the workflow. And I'll take an example from each of those two categories I mentioned, the HVAC equipment area and then the built environment. So we'll start with equipment. Let's go ahead and look at a blower. So we'll start in the software itself. As I mentioned, we're CAD embedded, so we're always going to be in a CAD tool. So in this case, in this example, it'll be Solid Edge from Siemens, that where the CAD resides. And if you have FloEFD, you get this additional add-ins, or there's a command ribbon here with the FloEFD functions, and you get an extra tab and tree over on the left-hand side related to FloEFD in your CAD environment. So as we start to go ahead and look at this model, and again, you're always going to work with the solid itself, the original CAD part. We do go ahead and add some lids. So at the openings of this, and in this case they're transparent, so or semi-transparent, so they're a little harder to see, but there are these two solids that kind of cap off our geometry and give us a model that we can analyze. That gives us this captured internal flow space. So the way a lot of our users start to set up a problem is to go through this wizard, and especially if you're not doing CFD all the time, it's this nice roadmap to get you on your way in setting up an analysis. So one of the first screens relates to unit system. So for an HVAC problem like this, you can go ahead and tailor it to a system that makes sense in terms of your units. Next, you'd start to define the problem a bit more with respect to the physics and what needs to be included. So in this example, being a blower, certainly we're going to include rotation, and so you can make a choice about how you want the rotation to be simulated in the analysis. So for us, it'll be this full transient rotation example. Go ahead and choose the fluids that are going to be included. So we'll go and pick air, and then you can go ahead and make a few more default assignments regarding the walls and initialization. And when you finish up, you get this project. So this is the first case that you would be analyzing for this blower. So what you can do from here, and of course we're in our CAD system, and so the user's familiar with how to manipulate the model and do things like changing that part there to be transparent, to go go ahead and make it a little more convenient to post-process and also finish our setup. There is a solid in there that encompasses the fan, the wheel, and the blades, and that's what we would use to set up our rotating region in this case. So you'd go ahead and just identify that component in your assembly and give it some information about the operating speed. So you can see we're assigning 37 RPM as our first analysis that we're going to look at with this example. Next, we would insert some boundary conditions. So basically, give some information about the openings, in and out of the fan here. So really, we're going to go ahead and just select those lids, and that's the other purpose of the lids besides sealing up the geometry. They give you faces to apply boundary conditions to, and we'll just open those up to the pressure conditions. Now, I said you don't need to create the volume for the flow space. If you'd like, you can visualize it, and that's what this check geometry tool does. So it gives you like this visual recognition of what FloEFD sees as the flow space. But you're not ever going to need to physically extract that yourself or manipulate it. It's just going to be along for the ride as you manipulate your solid geometry. Next would be assigning some goals, and this is a way to extract information of interest out of the analysis. So for this case, basically on the main openings of the model, we'd like to know things like flow rates through the openings and pressures, so getting things like a pressure difference across the fan. And really the last main thing prior to setting up or prior to running the model is to make some mesh choices. And more often than not, I and our users use the automatic settings. In this case, just to show an example of you do have access to the manual mesh settings as well if you get to a point that you'd like to invoke a little more manual control. So this is an example of showing that. So we've taken this is what's called the base mesh, so the starting cell size, and reduced their size, and even just a slightly more advanced example of including a local mesh where we're choosing a particular region that we want maybe a finer mesh. And in our case, it would be through the fan, the wheel itself, and resolving the flow in those blades more finely with the mesh. So we're invoking a local mesh in there. So really that's all there is with respect to setting up one of these problems. From here you would move into the running phase. And that's what this window is showing, and some of the typical things that you might have open during the run. So one would be a preview of the solution, so this real-time display of what's going on with the flow field, and additionally various graphs of interest. So those goals, like the flow rate through the blower, we could see how that's developing over time. And ultimately, as it flattens out, we achieve this converged solution, and we're ready to go ahead and start to look at our results. And so for that, you would be, of course, still in your CAD tool, in our case, still in Solid Edge, and you get to start to understand the performance of your design, right here on your native CAD model. So we're starting with flow trajectories, which are these nice kind of dynamic ways of visualizing the flow field through here. And with that, of course, we can start to add other post-processing capabilities or viewing methods. So next I've added a cut plot to the screen, which is basically just selecting a plane through the model and seeing the solution on that plane. In this case, we're looking at velocity. So the speed of the air as it's flowing through the fan blades and then ultimately out the exit there. You might look at things like separations and areas of stronger flow and uniformity might be of interest to you. So this is a way to start to visualize that. And of course, that's one of the key strengths of CFD in general, is just this ability to see the solution, where in other techniques like physical testing, it's more challenging to be able to visualize the flow. So that's one of the big things that CFD in general brings to the table. And of course, with FloEFD, that visualization is happening right here directly on your native CAD model. So even making presentations for customers or other colleagues in your organization that being able to see the solution directly related to the CAD model sort of is appealing or compelling. Another item that I've gone ahead and added to the screen here would be a graph of our goal. If you recall, we want to know things like what the flow rate would be through this device. So this shows sort of the convergence history, so as it reached that sort of steady value. And what we're doing now is just moving to what we call the Transient Explorer. Of course, if you recall, this is a transient or a time-dependent problem, right? So the wheel is turning and driving the flow. So we can save the solution at lots of different time steps and then be able to visualize the flow field at these different time steps. And this Transient Explorer lets you conveniently just slide back and forth at various moments in time. So from here, if you want to then start to test different cases, one convenient way to do that is to use our parametric study capability. So what a user might want to do would be logical in this type of problem would be to test this fan at different RPMs that it might operate at. So you can go ahead and assign a range of cases that you'd want to analyze. In this case, we're putting in the values directly, but you can also use, let's say, a range with a step as another way of inputting what RPMs you'd like to test. Identify the output parameters of interest, which would be those goals that we had assigned. And you get this table that summarizes then the different cases that are going to be analyzed. And you can go ahead and choose, let's say, how many simultaneous runs you want to do and how many cores on your system you want to use for the run. And it'll go through and then in an automated way run all those cases for you. And then from there, you can go ahead and sort of summarize the results of those various runs. In our case, we're looking here at things like flow rate for the different cases. That's basically as you increase the different RPM. Same with the pressure rise. You can see sort of the performance curves of this device. So that is taking your first example. Now from here, the obvious thing that you might want to do as a design engineer is make geometric changes to the device. And so again, the advantage of being CAD embedded comes through. We're using some of this powerful synchronous technology from Solid Edge to make this change here to change the number of blades in the fan that we want to analyze. So this would be, let's say, our second design that we are considering for this blower and understand the impact of changing the number of blades. So again, you would rerun that, and you can start to put these solutions next to each other and compare the performance of each one. So the one you saw a second ago was the original design, and then this is what that developing flow field looks like for this new blade design, and understand the impact of adding additional blades at some point. As you add more and more blades, you may start to get diminishing returns on how much more flow you're able to push through here. So you can compare these two devices side by side now. So that takes us through a HVAC equipment example. The next thing we'll look at will be the built environment, and this will be an office space and how that's being ventilated and cooled. This one we actually can have a bit of a more personal relation to, is that this is one of our Siemens offices. So we have people who work here that can give us feedback as to things like the comfort of the office and where there are hot zones and overly cool areas. So let's go ahead and start to look at what this model and this application might look like. So again, in our CAD system, in this case it's NX rather than Solid Edge, we can start to look at the model that's going to be analyzed. So you see sort of the full building being built out, but we're going to go focus the problem itself on the floor that has our particular office, and that has been set up to include things like solar radiation. So you see those gold arrows pointing down, so you can add radiation. And one of the convenient ways of being able to add it is to just choose a location and a day and time, and it will be able to assign the correct angle of the sun for that case that you want to analyze. So let's go ahead and look at this model a bit more closely and see what we've captured here. So this is the solid model of the space. We've assigned various relevant materials to the walls, to things like windows, to define the problem, the conduction side of the problem. There's a host of inlets and outlets throughout the office space here related to the HVAC system. So you have various vents and returns, and so this is going through and identifying those. Additionally, there'll be some locations that we have just pressure conditions that are open to environmental pressure. And then finally, sort of the main drivers of the HVAC system here would be these fans. And we're assigning this fan curve that's thermostatically controlled. So there'll be locations throughout the office space here that have temperature sensors, and as our analysis, as if the solution reaches a certain temperature, that would turn the fan on or off in the analysis. We have heat loads throughout, and so they're going to vary from one room to the other. We have a kitchen over here in the lower left-hand corner, or maybe a room with a lot of electronic equipment, so they may have higher heat loads than some just regular office spaces. And then we have a host of these points throughout the space that we have these goals where we're interested in calculating the temperature as well as their use for that thermostatic control that I talked about. So let's start to look at the solution. Here we have a visualization of the flow field, and the first logical parameter that you'd start to look at would be temperature. Obviously, in an HVAC application, it would seem natural to understand what the temperature field looks like through your space, and have warmer and cooler areas. This is a transient. So you see the arrow that's at the top showing you the direction of the sun as it's moving through the day. And as you look through here, you can see, as you move to different rooms, what the difference in temperature is in different locations. If you want to sort of more specifically call out the temperature, we have this probe capability. So you take your mouse and just take your pointer there and select different locations, and you can start to see specifically what the temperature is doing there. And again, play that as a time-dependent animation here, and you can see both the field changing as well as those probe values changing. Now, the range of temperature across here, it's not a huge range from, let's say, 24 to around 20 degrees Celsius, but temperature alone doesn't really fully describe what the overall comfort of the inhabitants would be. So this is where we can start to get into these comfort parameters and display those. So the first one we'll look at is something called draft rate. So draft is the unwanted local cooling of the body caused by air movement. So as you're being, say, blown on by a vent, that can be uncomfortable, let's say, and so the draft rate is defined as the percentage of people predicted to be bothered by draft. So you see those hot spots there. Those are areas where the draft rate is uncomfortable for the inhabitants. Now, another type of temperature or a comfort parameter that you would look at could be this mean radiant temperature. And this is measuring how much cooling or warming an occupant gets from this radiant heat exchange. So clearly over by the windows, you see by far the higher mean radiant temperature values as the sun shines in through the window, locally there. So again, you can use probes to see what those values are, and see how those change over time. You see as the sun starts to move that the angle of those regions changes over time. And then to start to combine those parameters, we could look at the operative temperature. And this sort of gives you the combined effect of both the convective and the radiant heat transfer. So starting to combine some of what we were just looking at previously with the two sets of comfort parameters. And then to quantify that in a different way is this predicted percent dissatisfied parameter. And it's an index that gives you information about the thermal discomfort or dissatisfaction by predicting the percentage of people likely to feel too warm or too cool. So those hot regions there are showing, a high percentage of people would either be, and it's not just hot, it's either too hot or too cold based on, those various parameters that we saw earlier. So you could start to interrogate your space and see where these areas of potential discomfort are relative to your HVAC layout. And another, taking that PPD parameter and quantifying it differently is this predicted mean vote. And what this does, it gives you a scale from -3 to 3, or in our case, -2 to 2, where 0 is neutral. And as you go to the warmer values, then the occupant is likely to be feeling discomfort towards the hotter side. And those blue regions would be where they'd be feeling cool, overly cool potentially. So again, these are sort of combining, these various parameters to sort of this one value to give you an understanding of how inhabitants would likely react to the HVAC conditions in a space. Now, of course, this is, you have the full solution available to you. So if you have a space where you want to understand more fully why you're getting that little blue zone of low predicted mean vote, you can go in and start to visualize the solution more fully. So we're looking at predicted mean vote here, coloring these flow trajectories entering the space. And you can see that where those blue areas are is where you'd have, some high draft rate for your inhabitant. So that's the kind of information that you can, extract, and the way that you would use FloEFD in one of these built environment type of applications. So the third and last example that I'll talk through here would be looking at a duct system within still that same office space, and showing how you can use the software in a more automated way to start to optimize something. So let's extract this duct and say that we want to, with respect to all of these outlets to the duct, achieve a certain goal. And so there's flaps at each of these outlets that would control the flow rate through the ducting system. And if we zoom in there, you can see, and this is just a simple case, but what it's going to be used for is just to illustrate this idea of being able to do optimization. So this is what our geometry and our flow field looks like, currently. Since we're in CAD, of course, the position of those flaps can be driven by an expression, in our case in X. So you can see they're all initially at around 10 degrees. You can put them in different positions. And we have requirements of these various flow rates. So we're actually not even looking for a uniform flow rate through all of the outlets. You have a varying set of requirements. So we can use, again, our parametric study interface, but what we're going to make use of is the design of experiments to do an optimization run. So you can define that you want to vary the flaps through a certain range of positions and what your goals are, and from all that it can do this sweep and ultimately extract the optimum case and put those those flaps all into positions that will that's the optimum positions to achieve those goals that you were trying to get with respect to flow rate. So for these ones nearest the inlet, the flaps are fairly closed, trying to limit the flow through there. And then as you start to, work your way through the system, the flaps would be more open as they are achieving the flow rate requirements for those particular openings. All right, so that's using design of experiments, which is, again, a capability that comes natively with the software. If you'd like to do a more sophisticated design exploration, we do have an additional module which is called Extended Design Exploration. And this makes use of the technology that is part of HVAC, which is another Siemens tool, which is this advanced multi-domain optimization software. And what we do is take the Sherpa optimization methodology and incorporate that into the parametric study as another optimization engine rather than just DOE. So that is something that's available with FloEFD. So just to start to wrap up here, we just look at some customer successes and again, different application areas. This would be again, a built environment type of study. This is of a stadium in Moscow, and this was leading up to the World Cup in 2018, simulating flares and the smoke from them and how they would disperse through the stadium. Another one of our customers, this is a automotive supplier, Dr. Schneider. This is HVAC systems within automotive applications, of course, and you can see, their statement regarding, the use of FloEFD, how it's able to shorten, product development, save costs, explain and present the flow behavior to colleagues and customers. So this whole notion of being able to, do this CFD work, early and often. One more example, this is a fan manufacturer, and they use FloEFD to increase the thermodynamic efficiency of the fan up to over 80%, where historically the traditional designs could only achieve around 60%, and being able to save 15% electricity usage along the way. So just to sort of summarize, what FloEFD is all about would be this idea of being able to front load CFD into your design process. Certainly starting with embedding into CAD as one of its foundational aspects, not needing to simplify your geometry very much in preparation for analysis, which is a big time savings. The Smart Cells technology, the way the mesher is able to deal with that geometry that is still sort of the raw, just kind of native CAD geometry, and handle that and not have the user or require the user to have this meshing expertise, which is more typical with classic CFD approaches. An accurate and robust solver technology, and then, as you've seen in some of the examples at the end there, this ability to do this design space exploration within the tool. So that, in a nutshell, is what FloEFD is all about, and hopefully you see, how it can relate and apply to HVAC problems as well. So I thank you all for your attendance.
And with that, this officially concludes today's webinar. I thank you so much for joining us today. Have a great rest of your day.